Now let's look at some practice problems involving functions of two variables, some practice problems that are a little more difficult than the one in the previous video. First, we're going to look at atmospheric pressure given by the function P, which is a function of two variables, y and t. The function is an exponential function. We're going to have 950 plus 2t e to the y over 7. The pressure is going to be given in millibars, and this is going to be the atmospheric pressure of a weather balloon. This pressure is a function of its height, so it depends on how high off the ground the balloon is, and it also depends on how many hours have elapsed since its initial launch. And we're going to look at the hours from 0 to 48, so that weather balloon is going to be up in the air for 2 days, and we can track how much pressure it's tracking based on the number of hours as well as its height. So the first question is, what is the atmospheric pressure after 12 hours if the balloon is 1 kilometer above sea level? So this is just a question about asking to plug in some values. Our function, f of yt, we have that y is the height, and that's going to be 1 kilometer above sea level, so y equals 1. And then t is the time, and we're going to be looking at t equals 12 hours. So our function is going to be 950 plus 2 times whatever our t value is, that being 12, times e to the y over 7, and y in this case is this value of 1. So putting this all together, we should have 950 plus 24 is going to be 974 e to the 1/7 millibars. So now let's look at give the function of the atmospheric pressure if the balloon stays at 2 kilometers above sea level at all times. This is another way of saying, let's look at a cross section of f of 2t. And again, we call this a cross section. This is a function of one variable, and this is going to give us some more information, something that we're more used to look at this big function. So what this means is that we're going to plug in 2 for y. So this will be the function 950 plus 2t e to the, in this case, our y value is 2, so 2 over 7, which is a linear function. As our only variable is just multiplied by a constant. There we have. Maybe we think about this as a linear function if we look at this as 950 e to the 2/7 plus 2e to the 2/7 t. This is our slope. This is our y-intercept. And in this case, it really is just a line. Now let's do the same thing, but now let's fix a value of t. Because that's what a cross section is doing, is we're fixing the value of one variable so we can let the other variable range. So here we're going to say what happens, we're going to track the pressure only looking at t equals 10 hours. So this time y is going to range, and we're going to have t equals 10. This is another cross section, and this time we are going to plug in 10 for t. So this should give us 950 plus 2 times 10 e to the y over 7. And again, that 10 is what we plugged in for t. Simplifying this, we should get a 970 e to the y over 7. This is an exponential function. And these are cross sections of our big function, which is just p. So let's look at the graphs of these cross sections to get some more information here. First one was just a linear function, 950 plus 2t e to the 2/7. The second was an exponential function. And again, this can give you some information specifically when we have a height of 2 kilometers or specifically when we have a time of 10 hours. The goal of this chapter, again, is going to be that we are going to combine these and look at the function as a whole, but that is a difficult thing to start doing as this is going to be a picture of a 3D function, which is much harder to read than a 2D function. So we will often look at cross sections to get information. Our next example is going to deal with the heat index, which is a wonderful example of a function of 2 variables, and it's something that we all deal with in our lives. So first of all, let's talk about what the heat index is. The heat index, going to give in degrees Fahrenheit, is the temperature that it feels like outside. So although it may be 80 degrees, the actual temperature, because of the relative humidity, it may feel like much more than that. When it's very humid outside, it often feels like it's hotter than the actual temperature. This is analogous to the wind chill when we're talking about cold temperatures because the wind is something that affects how cold it feels. So in this, we have 2 different inputs. We have a degrees Fahrenheit, the actual temperature that it is outside, and then we also have the relative humidity, 2 different inputs here. So let's ask some questions here. If the actual temperature outside is 90 degrees with a 75% relative humidity, what is the heat index? So in this table, we're going to go to 90 degrees and note that we don't have a row for 90 degrees, so we're somewhere in between 92 and 88. And then same thing for relative humidity, we're somewhere in between our 2 inputs, 70 and 80. So let's kind of look at this. We're trying to figure out what is going to be the value. We're going to only be able to estimate this. We're not going to get an exact value, but we can get something maybe close. One way that we could do this is we could look at, since 90 and 75 are halfway in between those 2 values, we can look at kind of what's halfway in between these values. So we could say that this would be a 106 halfway in between. And for the second one, maybe that's halfway in between. So 121 minus 106 is going to be 15. And then we can divide that by 2. And we're going to get 7 or 8. And we can think of this maybe being a 113 or 114. Since this is just an estimate, we'll just use 114. We'll round up. And then our answer is what we're going to be looking for right in the middle there, which might be 106 plus 114 to show the algebra here, divided by 2, which will be 110. So note that when we have this table, we don't necessarily have all the values available to us, so we may have to extrapolate that data by looking at the average of the 2 closest values or looking at a pattern between the values. This may not be the only answer that's possible for this question, but it's just one way to go about it. All right, next question. Let's describe the heat index for different values of relative humidity if the temperature is 96 degrees. So erasing this table real quick. What we're looking at is the cross section when the temperature is 96 degrees. And note that in this table, we got some weird stuff that the domain of the function doesn't actually exist for some of these things. What is the case when we have these empty squares? Well, since heat index is what the temperature feels like, at a certain point, our bodies cannot perceive the difference between these really high temperatures. Or maybe what this really is, another way of thinking about it, is all of these blank squares are just extremely dangerous levels of heat index. And maybe if you think about in Rhode Island, having a heat index of 100 is a very, very, very hot day. And we're talking about heat indices of over 130, which would be almost unheard of and very, very dangerous. So we're not going to consider those values. So for instance, if I think about 96, the most relative humidity that I'm going to be thinking about is 80. So we're looking at a cross section here, and again, we're just looking at that column. Bring that column of values down here. That could be a description of what's going on. And I just realized this should not be a 40 right here, but something in between 99 and 118, less than 100, maybe 104 or something instead of 40. Then we can also look at a cross section of 60% humidity. And again, that can give us an idea of, if we know what the humidity is, the temperature might range and gives us different heat indices there. Last question we'll ask, and we won't write this one down, but we can say something about, what's a comfortable temperature for you personally? What would the temperature or the relative humidity have to be? So if over 100 degrees is a heat index that you're not comfortable with, then you can use this table, this function, to tell you something about what are comfortable values. So again, if you know that 100 is a kind of breaking point, then you know that there's this range of values that will give you a comfortable level of heat index over something that's not. Or we kind of already had this once. We have this extremely dangerous level, and maybe this in between represents just a dangerous level. So this is almost like deathly. This is a dangerous level. And then the rest are maybe more normal levels or just very hot days. Moving forward in this chapter, we're going to continue looking at functions of two variables, but now we're going to be looking at more calculus-like things. We're going to start with trying to understand functions with contour diagrams. We're going to jump to 3D space and try to understand the functions as a whole.